In the previous lectures, we have been talking about different terminologies which are necessary to understand the basic concept of chemical engineering. And now we will continue the terminologies, but the terms shall be essentially used in the subject of heat transfer. These terms include, first of all, energy. Energy is basically capacity of a body to do work, but in the chemical engineering, energy actually exists in two forms. One, it can exist at the boundary of the system, and in another way, it can exist inside the system. It means that energy can reside in two places. One is the boundary of the system, other is the body of the system. So, energy which can exist at the boundary of the system and the energy that can exist inside the system. The energy that exists at the boundary is heat or work. This can be either heat or work. That's why heat is defined as the energy intransient. Means the heat only exists at the boundary of the system. During the transfer of energy from surrounding to the system, it appears as heat at the boundary. Second form of energy is the microscopic energy. Microscopic energy is further divided into internal energy, and enthalpy. This form of energy exists at the boundary of the system. Microscopic energy exists inside the system. In addition to this microscopic energy, another form of energy called mechanical energy. This also exists inside the system. So, microscopic energy and mechanical energy exist inside the system, whereas heat or work can only exist at the boundary of the system. For example, we have a system and we want to transfer heat or energy to that system. The energy that exists here at the boundary is only heat, Q, or it can be work at the boundary. It can be done on the system or it can be done by the system. So I will not show arrows. And inside the system what happens is the energy stored energy. Stored energy can either be microscopic energy or mechanical energy. Microscopic energy can be internal energy or enthalpy, and mechanical energy can be kinetic energy or it can be a potential energy. potential energy. This is how energy is classified in subject of chemical engineering. Let's define each type of energy individually. Heat is the form of energy that is intransient, that only appears at the boundary of the system. Work is the form of energy that only exists at the boundary of the system. It is usually a product of pressure and volume. Microscopic energy is the form of energy that is because of the activity and of the molecules and structure of the molecules. Now, internal energy is the form of energy that is because of the activity of the molecules. For example, if you increase the energy of the molecules, the temperature of the molecules will be increased. This will result in increase in sensible heat of the system. So internal energy can be a sensible heat. If there is a phase change, then there will be no increase in temperature of the system, so there can be a latent heat change. Internal energy can be in the form of latent heat or it can be in the form of sensible heat. So enthalpy is actually a product of internal energy. This is defined, internal energy is defined by U, enthalpy is defined by H. This is usually the sum of internal energy plus pressure volume work. We will explain this term in later stage. Now comes to the mechanical energy. This is classified in two types. One is kinetic energy, which is due to velocity of the molecules, and other is potential energy, which is due to potential forces of the molecule. We come to the conclusion that energy that is called stored energy this stored energy exists inside the system, and that can be any form of the energy except heat and work. Another form is transient energy. Heat and work are the only forms of transient energy because these only exist at the boundary of the system. The sum of all the microscopic energy of the system is called internal energy. Internal energy is basically because of the molecular activity or because of the kinetic energy and potential energy of the molecules. For example, if we have here liquid inside the container, we add energy to the molecules of the liquid. The molecules shall, after getting energy, will start colliding with each other. So after getting energy, their kinetic energy will be increased because their they are colliding with each other. The frequency of collisions increases as the energy added increases. That results in increase in temperature of the liquid. So temperature of the liquid is increased. That's why sensible heat of the liquid is increased. So internal energy results in the increase in sensible heat. Another form of internal energy is because of the potential energy of the molecule. When we continue adding the energy until the intermolecular forces between the molecules become weaker and weaker, the potential energy among the molecules is reduced. So after getting dominant over the potential energy, molecules of the liquid get vaporized and change the phase. Such kind of energy is latent heat, and this is also a form of internal energy. Another form of internal energy is the chemical energy or bond energy. One is the latent heat, another is sensible heat, third one is chemical or bond energy. The energy required to break the bonds among the molecules of a system is the bond energy, chemical energy. And then is the nuclear energy. The energy required to break the bonds among the particles within the nucleus is called nuclear energy. So internal energy has so many forms. Then is the enthalpy, which is also a form of microscopic energy. And this is the sum of, this is internal energy, and this is enthalpy. This enthalpy is the sum of internal energy and pressure volume work. This term is actually the energy required to push the fluid to the system. So an amount of work is required to make the fluid move. So we add this with the internal energy, you get enthalpy. This is also called microscopic energy. Another terminology which is important to understand is the thermal energy. Thermal energy is the sum of latent heat and sensible heat. This is the sum of latent heat and sensible heat. And this thermal energy is very important while applying energy balance in the subject of heat transfer. After getting complete understanding about different types of energy, we are now on the stage to understand the first law of thermodynamics. First law of thermodynamics is basically the law of conservation of energy, which states that the overall energy of the system and surrounding remains constant. This is first defined on the closed system, a system to which mass cannot enter or leave, but energy can enter and leave. Such a system is called a closed system. There is no mass flow to the system, so mass flow rate is equal to 0, and there is no mass flow rate out of the systems, but energy can be transferred to the system. And we know that energy which can be transferred to the system, that can either be in the form of heat or it can be in the form of work. There is no any other form of energy that will be transferred to the system, because only work or heat can exist at the boundary. So any form of energy that is transferred to the system will be transferred in the form of either work or in the form of heat. So total energy of the system remains constant as per statement of the first law of thermodynamics. It means that total heat input to a closed system should be equal to increase in the stored energy of the system. It means that increase in stored energy, del E, or change in stored energy, more appropriately, is equal to net heat transfer to the system. Means if we add heat to the system and system do some work to the surrounding, that sign is negative. So the difference represents a net heat transfer. Sometimes this statement can be written as in this form, and we define W as if work is done on the system, this will be positive. Work is done by the system, this term will be negative. So here we are writing that work is being done by the system to the surrounding. Second statement of first law of thermodynamics is for open system. Open system is a system through which mass as well as energy can flow. So when mass flows to the system, there is some energy associated with that mass flow. Such energy is called energy advection. So the energy associated with the mass flow is called energy advection, and we will discuss this at the end of this open system energy balance. At the moment, we just need to remember that the energy associated with the mass flow rate is called energy advection. First of all, assume that we have a system. This is open system, so mass can flow to the system. It means mass can enter to the system. Also, mass can leave the system. There will be some velocity associated with the mass flow rate, and there can be some elevation associated with this point at inlet. Similarly, velocity at out and elevation at out. There is internal energy associated with the mass flow rate to the system. This is U at inlet. Similarly, some internal energy leaving the system is UO. The energy which can be exchanged with the system can be in the form of heat, or it can be in the form of work. Change in stored in energy of the system is del E stored, and this is sum of mechanical energy and internal energy. So the energy entering the system is also sum of mechanical energy and internal energy. More accurately, the energy entering to the system associated with the mass flow rate is the sum of mechanical energy and internal energy. Similarly, energy outflow associated with the mass flow rate is the sum of mechanical energy and internal energy. And energy that can also penetrate to the system through the boundary is either work or heat or both. So now apply energy balance to the system. Rate of input of total energy, which is sum of mechanical and internal energy. Total energy minus rate of output of total energy, which is again sum of mechanical energy and internal energy, should equal to total change in stored energy. Total change in stored energy is basically accumulation of energy. So we can replace this term with the accumulation of energy. In short, we have energy, total energy in minus total energy out change in energy or accumulation of energy. This is the sum of in and out is the sum. Basically, energy in is the sum of mechanical energy, which is the kinetic energy, plus potential energy, and the internal energy. Microscopic energy, actually, that is the enthalpy change. In the same way, out is also sum of kinetic energy, potential energy, and enthalpy change at the out. This is at the in, and this is at the out. Potential energy plus enthalpy change at the out. In the heat transfer subject, we essentially talk about the thermal energy, not any other form of microscopic energy. So, in the heat transfer subject, the total sum of kinetic energy, potential energy, and thermal energy shall not be constant. Very surprisingly, because the energy is also generated because of some other reasons. That is also depleted because of some other reasons. For example, we have a system here. There is a chemical reaction and energy is being generated here inside the system. Then the sum of potential energy, kinetic energy, and thermal energy in, and the sum of potential energy, kinetic energy, and thermal energy out will not satisfy the equations of the energy conservation, because here chemical energy also appears, which also increases the rate of accumulation of energy. So this generation term should also be taken into consideration while applying energy balance. So in such cases we write that rate of energy in minus rate of energy out plus rate of energy generation should equal to rate of energy accumulation. And this equation is exactly same as the rate equation we have already discussed for the basic concepts. So rate equations can be written for energy. We have now seen that rate equations can be written for energy. And this equation can also be written for momentum as well as for mass. So here in heat transfer we will discuss this rate equation in more detail. Let's write the first law of thermodynamics in more precise way. That is rate of energy in, that can be internal kinetic energy, that is of mv square, mv square plus mgz, that is potential energy, plus internal energy plus pressure volume work. This is basically microscopic energy, sum of mechanical energy and microscopic energy at inlet per unit. This is per unit mass, and that's why we multiply this with whole mass flow rate at in minus half m. We have to delete this because we are talking about per unit mass, and we multiply this with the whole mass. So half v square plus gz plus u at out plus pressure volume work at out. This is again multiplied with mass flow rate at outlet plus this is sum of mechanical energy and microscopic energy at in. This is sum of mechanical energy and microscopic energy at out. In minus out. Energy in minus energy out. Plus net energy transfer to the system through boundary, that can be in the form of either work or heat. Q minus W, we have already talked about the convention of the sign Q minus W, that should be equals to rate of change in stored energy or rate of accumulation of energy. Rate of accumulation. Now this, in the subject of heat transfer, this internal energy is essentially thermal energy. That is UT. You can write this UT, thermal energy. So this is the final form of first law of thermodynamics. If the system is under steady state, total energy in to the system becomes equal to total energy out to the system. There is no change in net total energy of the system. Then such a system will be under steady state and rate of accumulation will be equal to 0, and we shortly can write m dot minus W will be equal to 0. This is the final form of first law of thermodynamics, or the energy balance or the rate equations, which is very important to understand for discussing the further subject of heat transfer. Then we have a second law of thermodynamics. Second law of thermodynamics just indicates the direction of energy transfer. It says that energy always transfers from a body at high temperature to a body at low temperature, or in other words, it is transferred in the direction of decreasing temperature. This is the statement of second law of thermodynamics. And let's discuss the surface energy balance. If we have a body here, this is the surface of this body. This is the wall. This complete is the wall of thickness some x. But the thickness of the surface is very, very, very small. This is the thickness of the surface. This is very small, dx. Let's wall is as temperature T1 and the surrounding is at temperature T2. That's T1 is more than T2. So heat will be transferred from the wall to the surface and from the surface to the surrounding. Heat from surface to surrounding can be transferred in two ways, either through convection or through radiations. And heat to the wall is transferred essentially because of the conduction. Conduction. The energy stored inside the wall is negligible. So if we apply surface energy balance, we should write energy in to the surface should be equal to energy out of the surface plus Q minus W equals to accumulation of the energy. Accumulation of the energy or storage of the energy inside the surface is zero because surface is very small and it can be considered as object with negligible volume. So it will not contain so much energy. That's why energy stored into the surface is always considered to be zero. So surface energy balance results in Q conduction. So energy in minus energy out will be equal to zero for surface. So energy in is conduction minus energy out is convection from the surface to the surrounding minus Q radiation from the surface to the surrounding. In other words, Q conduction is equal to Q convection plus Q radiations. In short, we apply surface energy balance to these rate equations and we get this result. This general rate equation, energy in minus energy out plus Q minus W is equal to rate of energy accumulation. Since rate of energy accumulation is zero because this surface is considered to be an object of negligible volume, and energy in is the heat that is conducted through the wall to the surface. Energy out is the heat that is released from the surface to the surrounding by convection, and the heat released by the surface to the surrounding by radiations. So this is the final form of surface energy balance. We conclude our discussion here. In the next lecture we will discuss modes of heat transfer, and in the ultimate proceeding lecture we will be discussing more specific topics in the heat transfer.